Now, you'll be glad to know you probably very rarely have to calculate these kind of estimates of the variance manually. In reality, software packages will do this for you. So let's look back at our example of spending on healthcare and the impact on life expectancy. We've got an estimated coefficient of 0.972. But the question is, does spending on healthcare have any impact on life expectancy? If spending on healthcare has no impact, that would be equivalent to beta 1 being equal to 0. So we want to try and test the hypothesis that the true population beta 1 is equal to 0. If we knew the true variance of the error terms, then we'd standardize our estimate. We could take the estimated beta 1 hat, 0.972, subtract the hypothesized value and divide through by the square root of the variance of the beta 1 hat, and that would follow a normal distribution with expectation 0 and variance 1. However, we're almost always going to be using estimates of the variance of beta 1 hat and estimates of the standard error of beta 1 hat. So we're going to rely on statistical software packages to estimate this standard error for us. Remember, the square root of the estimated variance is the estimated standard error of beta 1 hat. So you'll often be given what the estimated standard error is, and it will often appear in brackets or parentheses under your estimates. So here, this 0.193 is the estimated standard error of beta 1 hat. This is the square root of the estimated variance of beta 1 hat. So we can plug these numbers into our test statistic and then compare with the critical value from the t-distribution. Now, if you're estimating this relationship in Excel, it will do all of the work for you. We can see that Excel estimates the coefficients. The estimated intercept here is 76.685. The estimated slope parameter on spending per capita is 0.972. That's indicating that an increase in spending per capita of $1,000 is to increase life expectancy by 0.972 years. But it also estimates the standard errors for us. These are the estimates of the standard error of beta 0 hat and beta 1 hat. So our estimated standard error of beta 1 hat is equal to 0.193. It also constructs the t-statistic, the relevant p-value, and the confidence interval on beta 1 hat. And the t-statistic that it constructs is the t-statistic relating to the test that beta 1 is equal to 0. So we've got our estimates, we've got our estimated standard errors. So we're going to need to construct a standardized test statistic. And the t-statistic, remember, is equal to our estimated beta 1 hat minus the expected value of beta 1 hat if the null hypothesis is true, divided through by the estimated standard error of beta 1 hat. Our estimated beta 1 hat is 0.972. The expectation of beta 1 hat, if the null hypothesis is true, we can just substitute in our hypothesized value here, which is 0, and our estimated standard error is 0.193, which gives a t-statistic equal to 5.04. We have 44 observations, but we've lost 2 degrees of freedom by estimating a beta 0 hat and a beta 1 hat, so we've got 42 degrees of freedom. We would need to compare this t-statistic with the critical value from the t-distribution with 42 degrees of freedom. Now, with 42 degrees of freedom, the critical value at the 5% significance level is approximately 2.02. Because our t-statistic is larger than that critical value, we can reject the null hypothesis that spending on healthcare has no impact on life expectancy. Of course, our assumptions might be wrong. The estimates that we have might not be causal. If they aren't, then all that we've been able to show is that there is a correlation between the two. What we will explore in later sessions is how we can evaluate whether or not the estimates are causal and what we can do to try and mitigate against bias that might exist.